Good morning, students. Continuation of the previous topic, the rotational motion and the system of particles. In this, we are discussing the rotational dynamics. This rotational dynamics deals with the torque and angular momentums, moment of inertia. We are going to discuss later. Equilibrium of a rigid body. If you want to keep the object at equilibrium, we discussed many types of the four motions, but in this basically we have the translatory motion and rotational motions. Translatory motion means particles of all particles of the object moving parallel to each other with the same velocity is called the translatory motion. What are the velocity of the center of one particular middle velocity is there? Every particle has the same velocities and move parallel to each other. This is the translatory motion. Whereas rotatory motion, the object is rotating about a fixed point. That is, point is on the axis of rotation. It may rotate like this. I am taking this as a fixed point. That may not be at the center, that can be anywhere. So if I take the object here, apply the force here, it starts rotating about this point. That point may not be at the midpoint. So in this case, if the equilibrium means there is no resultant motion, or if it is moving to uniform velocity, both cases are there. So if you want the object at rest to move to get the translatory motion, then in that case the force need to be applied on this. The net force is not zero, then object will have the translatory motion. This force is F1, this force is F2. If F1 is greater than F2, object will move parallel to move along this F1 larger force. And if object force is applied about the center of mass or center of gravity, the forces are acting along the center of gravity, unequal forces are not keeping the object at rest. That means the force F1 is greater than F2. In that case, object will have the translatory motion. Once again, if I apply the force through the center to the point through the center of gravity, the object will have the translatory motion. Maybe many forces are there. The resultant force we need to consider acting through that center of mass or center of gravity. Equilibrium of the rigid body cases. First case we have to take is the no translatory motion. If there is no translatory motion, means F net force must be zero. That means net force is zero, the resultant of the forces along the x-axis, y-axis is also possible. In that case, there is no motion on the x-axis, there is no motion on the y-axis, means net force F net equal to 0 along the x-axis as well as y-axis. But if it is not having the translatory motion, it is possible that it can have the rotational motion like fan. Fan is not having the translatory motion, it is rotating at one place only. That means the rotational motion also, if you want to avoid, what you have to do is, you have to take the net torque net equal to 0. If these two conditions are satisfied, we say the rigid body is at equilibrium. What is a rigid body? Any hard body, so which keeps the distance of the particles constant even if the force applied. That is called as a rigid body. The distance of the particles should not change. Any hard body can take, they are supposed to be rigid bodies. Solid bodies we take as rigid bodies. So in this case, if the rigid body is at equilibrium, then it should not have translatory motion and rotational motion. If rigid body is at mechanical equilibrium, then if the rigid body is at mechanical equilibrium, then it must not have translatory motion. It must not have translatory motion, means net force is equals to 0. Or we can call it as it is a translational equilibrium and rotational equilibrium also called as. Must not have translatory motion. It is called as a translatory equilibrium. That means if net force F net equal to 0. If net force is 0, the object is said to be in translatory equilibrium. But if the forces are acting along the three-dimensional planes, if you have taken F net equal to 0. In a three-dimensional plane, if you have taken, in three-dimensional cases, if you have considered, the net force can be along the x-axis, y-axis and z-axis for n particles. no, sorry, for n forces we can consider forces in 3 dimensions. F net equal to 0 means sigma f I x along the x axis equal to 0. I can take the values 1 to n. The force acting along the x axis it means, and sigma I equal to 1 to n f I y equal to 0. This is for forces along x axis. It can be along the plus x axis, minus axis. Means sigma if you are taking means along the plus axis force and the minus axis force equal and opposite. So net force is 0. Similarly on the y axis also forces may be there. So net force along the y axis is also equal to 0. This is for forces along y axis. Similarly sigma I equal to 1 to n f I z equal to 0. This is for forces along y axis. These are conditions for translatory equilibrium. There is no translatory motion, but object can have the rotational motion. For rotational equilibrium, what is the condition required? Is net torque is 0. This is for must not have translatory motion. So object it must not have rotational motion also. Rotational equilibrium. Then net torque tau net equal to 0 we have to take for n torques. And one more thing is that must not have translatory motion. It can be in translatory motion equilibrium in the sense net force is 0. When net force is 0, object at rest means it will be at rest. If it is already in motion, then it will continue with the uniform velocity. It means must not have translatory motion means that it can have the translatory motion, but if it can be the translatory motion, velocity it should be constant. In this case velocity should be constant or velocity can be 0 also. Both are possible here. Must not have translatory motion, it can be translatory motion. Actually this point is not perfectly right. This one is correct ones we need to consider. But if object is at rest, then first point, this point also take. If object is at rest should be at rest only. Velocity is 0. When velocity is constant means that time also net force can be 0. But means velocity net force is 0 means acceleration is 0. When acceleration is 0, velocity is constant both in magnitude and directions. Next is it must not have the rotation motion. Same applicable for this rotation motion also. Rotational equilibrium is actually correct ones. Rotation motion should not be there means if initially at rest, it should be at rest, like fan at rest, or moving with uniform angular speed. Then in that cases we need to consider the rotational equilibrium. That means it can be at rest or it will be moving with a constant angular velocity. That means omega is 0 or omega equal to constant. That is related to the rotation motion. Then what is the condition required is net torque tau net equal to 0 is the condition required. Here net force is 0 required. Separately for the x axis, y axis if you are taking means the net force is the sum of the net force, vector sum of the force along the x axis, y axis, z axis. So individually all forces must be 0. We can take for n torques in 3 dimensions. For n torques in 3 dimensions along the x axis, rotation possible along the x axis, y axis, z axis. So we take the terms as sigma tau ix I equal to n, and these points will not be asked, only you have to write the statement. Net force is 0, net torque is 0. They will ask you what is the condition required for the equilibrium of the rigid body. One is translatory equilibrium, net force is 0, and rotational equilibrium. What is written in the bracket, that only you can write mention. For rotational equilibrium, net torque is equals to 0. These are independently terms, extra points you can take them as. I equal to 1 to n for torques, tau I y equal to 0, sigma I equal to 1 to n torque Iz equal to 0. This is for 3 dimensions. If 2-dimensional plane if you have taken, only x and y plane if you have taken, the net force along the x-axis must be equal to the net force along the y-axis only, we need to consider it. But with the forces acting, take a rod, suspend the forces F1 left side, I'll write this as some weight, that is giving the weight W1, I am writing is equals to F1. This side some other place, suspend the weight, another weight, that is weight is putting the force equal to F2, and support at this point. About this point the object is able to rotate freely. This point is also called as a pivoted point, it is also called as a fulcrum. About this point the rigid body or rigid rod is able to rotate. So this one is trying to rotate in this direction, weight, and this force is trying to rotate in this direction. About this point O, the rigid body is in equilibrium and force acting upwards is a reaction force, we take it as a normal reaction R. So it is equilibrium means what, upward force must be equal to downward force, and anti-clockwise torque equal to clockwise torque, means the way of rotationing. The distance from F1 to this point O, I can take this as equals to R1. This force due to the distance from where it is acting is equals to R2. Then for the mechanical equilibrium, what we discussed is there should not be rotational motion, there should not be translatory motion. Rotational motion means net force equal to 0. This is only in the xy plane we are taking. There is no way of chance of moving left and right side, so it has to move only along the y-axis, vertically we can take. So upward force must be equal to downward force. The normal reaction R is supposed to be equal to left side force is F1, right side force is F2. These two forces are pulling it downwards, but it is not going down. So balanced by the upward force, that is called as a reaction force. Weight is acting downwards is action, upward force is reaction. But if the rod is having the weight, we can consider that also downwards, W. Then plus W it becomes. Total force acting downwards is equals to total force acting upwards. Or we can take this as equals to R minus F1 plus F2 minus W, or plus W. Or if you take this bracket minus inside, minus F1 minus F2 minus W equal to 0. This is indicating now that net force equal to 0. Reaction is also a force only normal to the surface called as a normal reaction. Net force equal to 0. This is a condition required for the translatory equilibrium. That means it's not going up or downwards along the straight line path. But if you want to take the rotational equilibrium, what you take? Rotational equilibrium, this is for translatory equilibrium. But if you want to take consider the rotational equilibrium, if you want to consider rotational equilibrium, what you take is torque should be 0. What is the torque acting here? Torque is nothing but equal to force into perpendicular distance. The force is F1 acting here, and perpendicular distance from this axis of rotation is R1. So what I take is nothing but equal to tau 1. Because of this torque is rotating it in the anti-clockwise direction, opposite to the clock needle movement. These are 12 clock needles rotate like this, not in opposite direction. So this is called as a clockwise movement. Opposite direction is called as an anti-clockwise movement. So this F1 is rotating in this direction, anti-clockwise direction. So the torque because of F1 is nothing but equal to F1 R1. In this case, net torque equal to 0. One torque is because of F1, that is F1 R1. And this is positive we take. Anti-clockwise direction we take it as positive ones. Clockwise direction we take it as negative ones. So torque because of this F2 is nothing but equal to force F2 into R2 minus F2 R2. And normal reaction torque. This torque is equal to force is R into distance from the axis of rotation is 0. So because of this R, plus R into 0 equal to 0. Net torque is equals to 0. Why? Because it's not rotating. Balance condition if you have taken, if it is not rotating also, not having translatory motion also, for a rotational equilibrium we mentioned, net torque is 0 means the torque which is trying to rotate clockwise must be balanced with the torque rotating in the anti-clockwise. So this torque whatever you know, now we are going to call them as a moment of force, or simply called as a moment, called as a clockwise moments and anti-clockwise moments. Clockwise moment means force into, it is a torque only produced by force into radius or perpendicular distance. Trying to rotate in the clockwise direction is clockwise moment, opposite direction is anti-clockwise moment. So this moment of force, which is nothing but torque, is F1 R1 is the anti-clockwise moment, F2 R2 is a clockwise moment, and the torque because of the normal reaction is 0 because the force is acting through the axis of rotation itself. Similarly W, weight is also acting from the axis of rotation, that is also plus W into 0 is equals to 0. Net torque is 0 at rotational equilibrium. This part is 0, take it out. So what you get is F1 R1 is equals to F2 R2. That means these are clockwise moments equal to anti-clockwise moments. Sum of the clockwise moments, if instead of that many forces might be acting, sum of the clockwise moments equal to sum of the anti-clockwise moments. This term is called as this, what we discussed it. It is also condition for the keeping the rigid body at equilibrium, but this is called the law of principle of moments. It is called the principle of moments and law of parallel forces. Law of parallel forces I have discussed the same thing as a different way, but principle of moments we have to discuss. Principle of moments. It is like the equivalent of rigid body and mechanical lever and mechanical lever. Principle of moments and mechanical lever. What is the principle of moments is, we are talking only momentum, not forces. So if the object is having the no rotation motion means sum of the clockwise moments equal to sum of the anti-clockwise moments. That is called as a principle of moments. This may be asked for definition for 1 mark question. If the rigid body is under rotational equilibrium or is having rotational equilibrium, if the rigid body is under rotational equilibrium, then net torque is 0 and sum of clockwise moments equal to sum of anti-clockwise moments. Sum of clockwise moments equal to sum of the anti-clockwise moments. That is for moment here, only just moment if we said means that is nothing but torque only. Trying to rotate clockwise direction is clockwise moments, opposite direction is anti-clockwise moments. Where we use the principle of moments is it is used in mechanical lever, seesaw, common balance. They will ask you this principle for 1 mark or 2 marks questions, the principle where it is used. So take it as for 2 marks. And this we are going to discuss separately, mechanical lever. mechanical lever principle, working principle. It is a device. It is a device containing the parts. 3 parts will be there. The parts we'll discuss later. It is a device which is used to lift heavy objects with the less forces. And in that different types are there. One type only definition I am giving. It is a device or mechanical arrangement, we can say, used to lift heavy loads or heavy weights with less force, called as a effort. Principle, working principle. Principle of moments. Principle of moments is also called as the law of moments, meaning is same only. It works on the principle of law of moments. Okay. Principle of law of moments or some principle of moments. Principle of moments means the torque only. Here just moments means moment of force. That means force into perpendicular distance, or you can talk it as a torque. And condition what we take is clockwise movements are taken, anti-clockwise movements generally, not compulsory fixed, but generally what we take is anti-clockwise movements are taken. These points, please extra point, they will ask you for 3 marks question for the working principle, mechanism, and derive the expression for the effort. 3 marks question. These points you don't mention that. This is for our understanding purpose. Moment means moment of force, what term we are using. Another thing is clockwise movements are taken as a negative, anti-clockwise movements are taken as positive. Generally, not compulsorily, but generally we take it as, in some textbooks what they mention is in that way they mention it, sign convention. Generally, anti-clockwise movements are taken as positive, and clockwise movements taken as negative. Parts. And lever, this lever, it is not a human organ, that is lever inside that body, that is not, that lever is different, this lever is different. Parts. Load, it is a weight lifted, weight to be lifted. Effort, it is a force applied to lift the object. Force applied means external applied, external force. Fulcrum. It is a pivoted point about which the rigid rod are able to rotate freely. Fulcrum. It is a fixed pivoted point about which a rigid light rod can rotate freely, please. Another one is actually three points only. They will ask you what are the parts of the mechanical lever means load, effort, fulcrum. 3 only you can mention, but we are going to use to apply these things now. We require very light rigid rods. Light means negligible mass. It means light rigid rod. It's compulsory required to apply these forces. Archimedes used this mechanical lever mainly. Diagram for this AB. This AB is a rigid rod, and you are keeping some load here, some stone or something. This is going to be mg. Weight is equals to load, and force applied this side to balance it. Weight is acting downwards, mg, and force you are applying it, pull it downwards. It is like this. The weight is here, trying to pull it like this. So to balance it, you are applying the force other side. What about this one? That is going to be the fulcrum. About the fulcrum, this fulcrum F. The weight normal reaction is acting down upwards. Normal reaction symbol can be taken Kaplan. In the textbook they mentioned take it as R, and this is a force applied. It's nothing but called as a effort. It is also downward. This is also downwards. This is a supporting point related to fulcrum. A sharp edge, rigid support we are taking here. About this, the rod is able to oscillate or rotate. The distance from this fulcrum to effort is called as effort arm. This is called as a effort arm. This is called as a load side distance, is called as a load arm. Effort arm, load arm. These are the 3 parts: effort, load you are lifting, and fulcrum are the 3 points we require, and R is a normal reaction here. R is normal reaction, and AB is rigid light rod. Mass neglected. Neglecting mass means its weight should not be considered. Mass. F is effort, that is a force, and the mg is taken as a W. It is nothing but a load. Load word sometimes only for mass also load is used. The total weight W also load is used. You have to be careful. At equilibrium condition, if you are taken, means upward force equal to downward force. Upward force is R, downward force is F and W. I will repeat this in the next class. We will stop here.